Yeah, and he runs our machine shop as well. So in the basement of Steward, there's a machine shop. Maybe some of you have met Mario or met some of the guys who work for him. So again, a lot of really good knowledge and background in ground-based and space-based telescopes. Additionally, in ETS, we have Victor Gasho, who is a project manager. Does a lot of the high-level project management work, has a good background in radio, antenna and telescopes, as well as some ground-based optical telescopes and space-based telescopes. He's currently heading up a bunch of things at Steward, including the GS comparison. And then additionally, John Ford, who has joined us. He is a senior electrical engineer, and he will give you his wonderful background in, he will be able to assist with his wonderful background in electrical engineering on lots of ground-based and space-based telescopes as well. So we've got a really good core group of engineering team here, and we're happy to help you guys out with your project and hopefully see it through to a successful completion. It looks like a fun project.
Thanks.
So if you guys want to go around real quick and just give us kind of who you are and what you're doing, that would be cool. So we know who you are.
Okay. I'm Bridget Norman. I'm the systems engineer, and I'm the team leader of this project. Mason, you can go next.
Okay. Yeah, I'm Mason, and I am the optical engineer of the team.
I'm Carrie, and I'm one of the electrical and computer engineers for the team.
I'm Jared. I'm one of the mechanical engineers working on the team.
I'm Elizabeth, and I'm working on mechanical on the team.
And I'm Shangray. I take care of the electrical stuff on this design.
I'll introduce myself too. I know most of you, I think. I'm sponsoring this project as part of an NSF grant that I've got. What a part of our project was to build an outreach telescope for student and public use. And so I've sponsored this capstone team to design it, and I've been working with them for the last, 6 months now?
Yeah.
Since August-ish. Yeah, it's been a bit.
I'll introduce myself as well. I'm a research assistant under Justin Hyatt working on a similar project, and so he invited me to come here so I could learn from the capstone team. So I'm here just to learn.
That's very exciting. Well, welcome everybody. I'm very glad to host this. Why don't we just go ahead and dive right in? Bridget, I saw you sent me over a new presentation. Do you want me to share? Do you want to share?
I can share. I can go through the slides.
Yep, I think that's probably a good place to start so that we can get everybody on the same page.
Awesome, cool. Let me just.
Hey, Carrie, I have a question. How do we provide comments for each slide? I don't want to interrupt presenters, but I know we'll have some comments. How do you want to handle those?
Well, that's a good question. So before we jump, I guess, let me give you a little bit of background on what happened. The student team submitted this same presentation with a few before the tweaks to the safety committee through Mark Buglewitz. Mark presented it to us and asked us to look at it from a safety committee point of view. So a few people have already reviewed this and submitted some comments through that channel. Bridget's team was able to provide some feedback, and I sent that out to our ETS team on the call here today, just to give you guys a heads up on sort of the questions that have already been asked and the responses that were received from the student team as well. So I think in some cases, Tom, I did look through your comments a little bit. I think in some cases, maybe some of your questions will be answered by those documents. Additionally, I can compile the questions that come up on the side independent of this presentation, and we can resubmit to the students for comment after the close of this meeting. I think it's probably best to push through the slides as a set before we start diving into detailed questions on each slide, because I agree with you. I think interrupting the slides would be, it may lead us into a path where this meeting could take like 6 hours, which I don't want to do.
Very good, thank you.
Okay, so I think, yeah, let's just save questions until the end if there's detailed questions we want to talk about.
Yeah, we can definitely do that. We're used to that with our engineering class. We usually take them afterwards. So that usually saves time.
Okay.
I'll just get started. So this is our critical design review with updated slides from when we first sent in a presentation. So we have added some things here. We've included some more pictures and analyses. So we'll give the presentation now. So we're a senior design capstone project for engineering, the College of Engineering. And we've already introduced ourselves, so I'll just go to the intro. So what our project is that we are designing a radio dish and truss structure that will be put on top of a pre-existing radio telescope mount. Currently, that existing radio telescope is being reused from the Chris Walker's radio telescope. He's from Steward as well, and it was operated until about 10 years ago, and then it was put into storage, and we're now fixing it up. So we plan on having the telescope be able to move in all AZ direction again with sufficient pointing accuracy so we can drift scan targets like this, the sun, the moon, and galactic clouds. And we plan on, and the telescope will be a single off-axis parabolic dish. And Justin already pointed this out a little bit, but the radio telescope that we're building is intended to be operated not just by astronomy students or faculty, but also the public. So we want to open this up so not just astronomy, but also other students and faculty of U of A and in Tucson could experience radio astronomy for the first time. And we do want to add real quick that integrating a receiver into a radio telescope is not something in our scope. That is something that Justin will be working on with his team about. A couple of things that for our point design that we designed for Justin is that we wanted to demonstrate his new panel forming technology, and also part of this was also revitalizing the software and the hardware of the mount so that it can work with our new designs. So this is the pre-existing mount that we are working off of. This is currently in Steward Observatory room N601, so it's the top floor storage room. And so currently right now we have been revitalizing and using the existing power supply, servo motors, gearboxes, and limit switches for this radio telescope. We did fix up some of the gearboxes, and we'll talk more about what else we fixed, but we have done some updating from some of the parts of the mount just so we can reuse it again. So this
hey, Bridget, just a quick question on that. Do you know what Chris had, what size dish he had, and whether it was just on-axis, or did he actually have an off-axis design on that? Do you know the details on that?
We know it was made out of fiberglass.
Yeah, it's a 3-meter on-axis fiberglass dish.
Okay. All right. Thanks.
Yeah. Great question. So continuing, this is our system block diagram. The dashed lines include the system that we're working on, so that's our scope. So that doesn't include the amplifier system or the receiver, but it does include the Raspberry Pi, servo motors, brakes, and limit switches, which we're all fixing, and includes the brakes and power supplies. So, and of course the dish antenna, which is currently 2.4 meters. We'll talk more about this in the presentation. So these are our system requirements that Justin laid out for us and we wrote up. Our performance requirements, and we'll go into detail as well in the presentation as well with this. So performance requirements include the resolution, pointing, accuracy, and gravity sag. Our environmental requirements include the operational wind speed, survival wind speed, our ingress protection standard, the panel separation, the gaps in between each panel, lightning rods, we're expecting to put that onto our telescope, and stow pin, so to ensure that there isn't flying radio telescope on the roof of the building. We also include our safety requirements, which include the hazards lockbox, and we have an emergency switch. Our electrical requirements include the GUI, the limit switches on the mount, and the power consumption by which it uses, the telescope uses, and the optical requirements. That includes the wavelength that we are intending to observe, the aperture, illumination angle, offset angle, and the mounting location. And our mechanical requirements include the weight and the brakes. And we'll go more into detail about this. This is just, I'm just going over what our system requirements include.
Sorry, Bridget, to interrupt. You skipped over stow pin on the prior slide.
Yes, so I'll explain more. So yeah, it's a stow pin that basically prevents our the dish from spinning around erratically. So we'll explain more what that looks like as we go into the presentation. Mason will talk about that. Design details, Carrie will start talking about.
Okay, so on the next slide, it's a repeat of the picture we showed you previously. So this is a satellite view of the potential placement of the telescope. Option 1 is preferred because its view is less obstructed than option 2. We're currently in the process of determining which option or alternative would work. Also, the room in 601, there is a door that leads straight to the roof from right next to that room. So it allows for easy access to troubleshoot or remove or insert the stow pins. So the next slide shows a closer up view of the first option. And the dimensions for this pad is 10 feet by 10 feet. The second option on the next slide, as you can see, it's slightly smaller pad, and there's also a bit more obstruction. The solar tracker on the pad is our sponsor, Justin Hyatt's, and if that option is used, he has agreed to remove it so we can place the telescope there. On the next slide, we show the size and weight of the telescope. So it's almost 500 kilograms with the max height being just over 15 feet at stow position. And our stow position is 30 degrees past zenith. And its max breadth is a little over 12 feet, which is its hazard zone at horizon. So this is also why we prefer option 1, because its dimensions are slightly bigger. So it's easier to, so the pad kind of more inclusively shows the hazard zone than the 8 by 8.5 dimension for option 2.
All right, so here's our top assembly drawing. We've broken it up into 4 separate subassemblies. So first is our dish antenna assembly. This includes the trusses and the paneling that we're going to be making. Number 2, or that Justin Slive is going to be making, sorry. Number 2 is our mount subassembly. This is just, as we've stated before, the mount that's currently sitting in the storage room. Number 3 is our computer assembly, and number 4 is our power supply assembly. All right, so here we're going to break down a little bit more about what our dish antenna assembly is. So the dish antenna assembly is primarily 4 vertical struts. If you look at the top assembly on the left-hand side, 1, 2, 3, and 4, those are sort of the main vertical struts, and those will be connected together by horizontal angle irons. Additionally, each of these will be connected to the mounting plate. Additionally, we will have 2 receiver arms, 5 and 6 on the bottom. And those are actually detachable, and those are just going to be where the receiver is going to be placed when it's eventually made.
So this is our SRT mount assembly. The first part is the mount central structure. The second part is the mount legs. The third part is the mount alt AZ structure. The fourth is the mounting plate. The fifth is the servo motor. 6 and 7 are the gear reducers, and 8 is the anemometer. I just want to mention that the only thing we changed in this assembly was the counterweights, since this is designed for a new and heavier dish.
So in terms of the operation of our telescope, I think the slides are a little backwards. When we're operating the telescope, the stow pins are going to be removed, but anytime the telescope is not in operation, which is going to be a majority of the time it's sitting up on the roof, these stow pins are going to be in the telescope to kind of be an extra fail-safe should brake failure occur or, unexpected apocalyptic hurricanes hit Tucson. So what we have is a stow pin on the as structure, and as you can see on the kind of diagram over to the left, this stow pin right here goes straight through the central structure, which will stop it from rotating around. And then we also have a stow bar that connects the counterweight arms to the actual mount structure itself at stow position. And this will limit the azimuthal motion. By having both of these stow pins in, it'll be a good kind of extra fail-safe. Next slide, please. So once again, kind of going to the operation plan. So whenever someone has to use the telescope, it will have to be completely de-energized, and we're using a lockout tagout procedure to ensure safe practices and that no one can turn on the telescope and make it spin around while someone's out there trying to remove or put in the stow pins. So once the lockout tagout key is activated, the operator can go out onto the roof and remove the stow pins and bars whenever they need to operate it. And then when the telescope is stowed and powered off, which like I mentioned is going to be the vast majority of the time that this telescope is sitting on the roof, the stow pins are going to be on it, and the operator must schedule a specific time to be approved in order to use the telescope. As I've kind of mentioned, the stow pins are a manual thing. We need to have approval, lockout, tagout. So there's not really going to be much chance of this telescope kind of spinning around wildly without someone being fully aware of what's going on. I should also mention one other thing is if the power goes out, the brakes are clamped at no power. So when the telescope is powered down, the brakes are fully clamped on it in addition to the stow pins.
Okay, so here is the drawing for our computer subassembly. The mount will be controlled remotely from room N601 using the GUI on the computer. The electrical cabinet displayed is NEMA 4 rated, and it will hold the Raspberry Pi, the Arduino Nano, and the brake controls. And then the Raspberry Pi will connect back to the computer, which will allow for precise control and monitoring of the telescope. Please note that this is the same electrical box that is shown on the next slide, but we separated the drawing so we could show to you guys in more clarity the separate sub-assemblies. So Shangri will go into the electrical, the power supply.
So this is the power supply assembly. Its main purpose is to deliver power to the telescope and providing safety features. So this electric box in the picture, it will be NEMA rated. I think it's 4, so it's IP66 equivalent. So it's water type. Water and dust is difficult to get in. And you can see we have a disconnect switch with the lockout hats on it. Whenever you want to perform maintenance, say remove the stow pin, place the stow bar, it needs to be lockout tagout. When this lockout tagout is activated, the telescope will be de-energized completely. Nothing is going to move. We also have a e-stop on there in case somebody is around and they want to shut the telescope off. And we have the 2 green modules. They are really mounted on the telescope chassis. We just showed it for the purpose of showing. They are responsible for dissipating the back EMF when the servo motor is decelerating.
Ingrid, can I just point out one thing? The lockout tagout will be always engaged unless someone is actively using the telescope. So there will always be a padlock there.
Yeah, and when the padlock is there, the telescope will be completely de-energized. And this is the electrical schematic. We borrow a lot of design from the Bio2 radio telescope. This is the schematic for the control room. On top of it, say this part, is 3 buttons. The first one is the enable button. So if you want to use it, this button needs to be closed. And the second one is the e-stop. This one would be the big red one. It has to be turned, reset. And the third one is the watchdog circuit we borrow from the Bio2 design. This is separate from the computer control system. If the telescope stops receiving this watchdog signal from the control room, the telescope will also be completely de-energized because the active communication has been lost. And here is the schematic diagram for the remote side, which will be located on the telescope. Let's see, annotate. So here would be the relay, aka the e-stop loop. They will be responsible for breaking the power to the servo motor in case any of those buttons are closed or tripped. We also have a limit switch. This one is a stow bar limit switch for the azimuth. If the stow bar is still in place, the telescope will still be de-energized unless this stow bar is removed. And the same thing goes on for the azimuth. The first one is the altitude stow pin limit switch. If the stow pin is left in, you cannot turn on the telescope. The second and the third one, they are limit switch. Just limit the physical travel of the antenna dish so it doesn't crash to the floor or go too far that is out of the mechanical travel of the telescope.
How do you limit the azimuth travel?
So far, the azimuth limit is done by the software. In the software, we just say if the telescope has been turned 360 degrees, then we say it exceeds the limit. The main constraint is the cable twisting because we are cable feeding through the meter of the telescope. That's the main constraint. But altitude, that would be physical limit switch.
Yeah, I think you're going to find you want an azimuth limit switch as well, because you'll twist your cables off at some point if you don't, especially if you have untrained people using it.
We have a solution. We don't have a physical limit switch, but we have a software limit switch. The physical switch for the azimuth, that's for the stow bar. If the stow bar is left in, then you cannot turn it on.
You also have a limit switch for travel limits on the elevation.
Yes. Elevation has a physical limit switch. If it goes out, it cuts the power. Okay, so this is the control system or the GUI we have so far. On the left side, this is the main control. We can enter the coordinate. So as of now, it's AZ elevation. If you enter a coordinate, it's going to move to that. We haven't finished the tracking software yet. That's part of because it's kind of outside the scope, but we're working on it. Clear this. Okay, so the next part is the safety features. We have a telescope stop. If there is an ongoing motion of the telescope, if you hit this button, it's going to stop the telescope. Stow, we will cover stow in the next slide, and jogging features that allows you to draw the telescope using one of the 4 steps. Have a degree at a time, 1 degree at a time, and so on. And last, we have the system settings that just turn off the software features. So when you don't want to accidentally hit something, we can turn off the control completely, or turn off the servo motor control or the jogging feature so we don't hit things when I don't want to. And at the middle, we have 2 dials to indicate the actual position of the telescope without looking at the physical telescope. So you have an idea in your mind where the telescope is pointing at. And the right side, this is the debug information. Just shows we are communicating with the telescope correctly. And it also shows variety of debug information about the telescope. For example, this one is what is the current status of the motor, if there's anything wrong with it. And on the next slide, we have the stow. So this is also a very important safety feature. This is because our telescope is off-axis design, which means when the telescope pointing at the zenith, that is not actually the place where the cross area is minimized. It's actually a little bit past in the zenith. So what this does is when you want to shut off the telescope, you have to turn the telescope to the stow position. In our case, that will be 30 degrees past the zenith to minimize the cross area. So the wind load is going to be minimized and so on. The software is also recording the absolute position of the servo motor and its motion velocity every 2 seconds. That way, if the power to the telescope is lost, experience a power loss, we still know the last position of the telescope, and then when the power is come back on, we have a way to recover it using the stow telescope and the jogging button to get it dialed back in.
So here we have a short video showing just the jogging feature of the GUI. So as Changri mentioned, first you must enable the servo motors and enable jogging. And from there you can do jogging in degree increments from 0.5 degrees to 10 degrees. An operator can jog the mount in both directions at the same time. So here we can see we're moving both in the alt and the AZ direction. And not shown in this video is the coordinate entry feature, which Changri mentioned before. And that allows the user to input specific alt-AZ coordinates, and the axes will move to the inputted coordinates correctly.
Can I ask, that's a nice video. What speed does that represent?
I believe that's, we currently have the velocity as 2 RPM. It's easily changeable for however fast or slow we need it. We know that generally it might want to go a little bit slower, but that is something that's easily changed in the software if as needed.
Yes.
For testing, sometimes we will change the velocity and acceleration.
And also, this video is a little bit speeded up, so the actual thing is going to be slower than the one in the video.
Thank
Yeah,
you.
I think,
yeah, that was my question, is the video speed. The presented video is actually sped up. Very good.
Mm-hmm.
Okay.
And in your requirements, did you have a maximum velocity rate or acceleration rate that you guys want to move this dish at?
we don't have that in our requirements, no.
Okay.
No, yep.
Slow and steady. That's
All right, so you're not tracking Leos.
that's not the plan.
Okay.
I think we might want to track the sun or the moon or something like that. I think that's the best we might get.
Good ephemeris objects, right?
Okay, so moving on to our safety considerations. We have an emergency stop on the electrical cabinet at the telescope. We have an emergency stop in the operating room, which is the same design as the Bio-2 radio telescope, as previously mentioned. There's a software emergency stop on the GUI. There's a disconnect switch with lockout hasp connected for lockout tagout protocol. If disconnect switch is disconnected, the entire system is de-energized. Our factor of safety was at least 5 for all structural requirements under survival wind speed conditions. Our assembly will be on the 5th floor roof, which follows and is set up for all safety protocols. All components can easily be moved from base floor of Steward Observatory to the roof. Our sponsor plans on painting a hazard zone circle around the telescope to prevent people from entering. Power will be connected to an existing junction box on the pad. We will need to run a short conduit from the pad to the hut that contains an Ethernet cable. We will work with Mark to communicate this design to facilities management to see if they would like to install it or have us install it. Maintenance will be conducted as needed by Justin Hyatt's research group, and the material of the roof pad is to be determined.
So now we're going to get into some of the analysis and prediction of performance for our telescope. So to start off, I have kind of a full table here that goes over all of our system requirements that we verified via analysis, because it's kind of a large portion of our project since we're designing this very large dish and support structure. So for resolution and pointing accuracy, these are pretty much just kind of system parameter based, wavelength and size of the system, and these meet the predictive margins we need in order to look at things like the sun and the moon and larger objects. Gravity sag, operational, and survival wind speeds. All of these requirements were tested with SolidWorks FEA, as well as a little bit of ANSYS. So for the gravity sag requirement, we needed a 200 micron RMS deformation, and as we'll see in a little bit, we were able to meet that standard. For operational wind speed, we need to be able to be operational up to 5 meters per second, and this is going to affect the dish deformation, the individual panel deformation, and then the kind of sway of the mount. And as you can see, we meet all of our specifications here, so we should be able to track and have good optical performance at operational wind speeds. For survival wind speed, we have to have
I've got a quick question, Mason. Sorry. Did you include a safety factor in the operational pointing by chance?
Well, that's not really, it's,
Yeah,
we have the stress plots for, but we were just looking at strain because the mount's under more force under survival and it was fine there.
Okay, cool. I was hoping we might get a little bit extra because we don't need a safety factor for the operational. Anyway, carry on.
Like extra wind speed?
Sorry, we wouldn't need a safety factor for the operational pointing accuracy.
Yeah.
So anyway, I was just curious if we had included one or not, but that's
No,
fine.
no, we just looked at kind of performance criteria for
Great.
operational wind speed.
Great.
So for survival wind speed, as Justin had mentioned, we're trying to hit a 5 factor of safety at 25 meters per second. So using MATLAB, SolidWorks flow simulation, and SolidWorks FEA, we were able to put this requirement into realistic forces on our telescope, and we were able to find that the dish truss, panels, and mount all met this factor of safety requirement. Panel separation, we needed to have a sufficient gap to stop optical or to allow rainwater to pass through. It needed to be small enough to stop any kind of optical leakage on the dish. Next slide. For the wavelength, aperture, offset, and illumination angle, these are all kind of like design point things. So basically, whenever we created our model, we had to take these things into consideration. Illumination angle is one thing. Basically, as long as the receiver for the telescope the telescope was designed to have an illumination angle of 135 degrees or less. This is so it could fit the old receiver that went on the old telescope. So if we wanted to use that for 21 centimeter observation, we can do that. But our system has a smaller illumination angle, which basically just means that other receivers can be fit to it that might work a little bit better. For power consumption, we had to make sure that the power consumption that the motors take can be provided by the power supplies, and we were able to assure that. And then as mentioned previously, the mount structure and brakes were also analyzed. So the mount structure is just how the mount itself reacts to just the weight of the dish without any other external forces, just to make sure it can support that weight. And then we also tested the brakes, basically accounting for what would happen at survival wind speeds to see the torque put on the brakes and to make sure that the brake clamping force could withstand that torque. And we'll go into all these analyses now.
All right, so one of our performance requirements is gravity sag. So for this system, we're looking for a target RMS deformation of 200 microns or less, sorry, delta RMS deformation of 200 microns or less. Through simulation, we found that at the zenith, the RMS deformation was 126 microns, and at horizon, the RMS deformation was 250 microns. This gives us a modeled delta RMS deformation of 188 microns, and this is assuming that the dish panels are aligned to the least deformed position between horizon and zenith. All right, and similarly for our operational wind speed, we're looking for a target RMS deformation of 200 microns or less. Here we subjected the system to FEA loads of gravity and wind speeds of 5 meters per second. We tested these wind speeds at a variety of directions to see which one would perform the worst. And the worst case scenario out of all those directions gave us a zenith RMS deformation of 129 microns and a horizon RMS deformation of 253 microns. After correcting for alignment, this gives us a zenith deformation and horizon deformation of 191 microns, which is only 3 microns worse than just under gravity sag by itself.
Jared, just a quick question on your wind speed, for your structural, maybe you're going to get to that. Did you use the zenith pointing for your, I assume that's where you had the worst drag, given that you've got the most deformation. Is that the position that you used for the structural, for survival?
So survival, it's actually at zenith. Bridget, if you want to go back one slide. So if you look at on the left, that zenith position, 30 degrees past that clockwise, that gives us the least amount of cross area, or the smallest cross section for any wind loads. So that's where the wind loading, that plane is where the wind loading is coming in for our structural simulations.
So you're assuming that your survival, you're at stow.
Correct.
Okay. All right.
Can you explain why your zenith RMS deformation is worse after alignment correction than before?
Because we're aligning it to sort of the middle ground between zenith and horizon. So we label that as sort of negative deformation in the case of the zenith and positive deformation in case of horizon. So Mason, you might be able to explain like the whole alignment procedure a little bit better.
So you took the total and divided it by the center of travel. Okay.
Yes, exactly.
Yeah, so you're using a rigging angle is basically what they would call it. Okay.
Yeah.
Yep.
Next slide, please. All right, so this is our survival wind speed. As just stated, these simulations will run at the stow position at 30 degrees past zenith, which is the smallest cross section for any wind loading. The loading conditions we subjected to were gravity and wind speed of 25 meters per second. Similar to the operational wind speed, we conducted these simulations at a variety of angles to see which would perform the worst. So all of our dish panels are made out of aluminum 5052O, which is a yield point of 89.6 megapascals. The worst case scenario was a crosswind modeled stress. This gives us a factor of safety of 204 microns. So in no way are these dish panels going to be yielding in any way. All of our supporting structure, we've made it out of A36 low carbon steel with a yield point of 250 megapascals. In the worst case scenario, this was a crosswind breeze of 25 meters per second, and that gave us a modeled max stress of 48.1 megapascals, so a factor of safety of 5.19 in the worst case.
Have you done any analysis to see what would happen if you didn't get it stowed before you had a storm? Because that does happen.
We did not know.
I can mention one thing on that, and Justin, I'm sure what happened too. How the telescope's operated is that there's going to be weather forecasts and everything before anyone goes to use it, and it's not going to be sitting and operated for an extended period of time. So there shouldn't, with smart user, with a smart operator, there should never be a scenario where a rainstorm or something bad could happen when the telescope's at a different position, because it's always off and then turned on a clear day.
Well, yeah.
But you're not always going to have smart users. You need to protect your equipment.
Right.
And so I understand there's a sequence to stowing for survival speed. And that's what John was getting at. You have to anticipate it's time to stow. You have to put it and stow it at that minimal cross-sectional area to have these margins you list here. So let me ask, in trying to forecast, if you're operating, what is your speed, wind speed, where you say, okay, I'm going to shut down and stow? Is that at your max operational envelope at 10 meters per second?
Yes.
So if you go to 11 or 10.1, you say we have to stow.
Yep.
Correct.
So I don't know if you saw on the computer subassembly, but we have an anemometer that is programmed so that it's always reading in the current wind speed. So we have a software check so that anytime it goes past the operational wind speed, we will stow it. We'll get the current position and we'll move it to stow position.
The anemometer is located where?
That is currently to be determined, since it needs to be mounted on a specific location on the roof. But
it would be next to the telescope.
Yeah, but it'll be really close on the roof next to the telescope. So then we feed the cable into the electrical box on the Arduino, and then it goes back to the GUI.
Right.
So,
but just beware of when you go to define its location, you're pretty sensitive to wind speed off of the height of the pad that you mount to. So if your anemometer is located at the pad height, it will not be reading accurate wind speed. Just beware of that.
Yeah, we're aware of that. So maybe we need to raise the anemometer so that it's probably at the height of the dish antenna, or midway of the dish height.
And not close enough to it that the antenna itself will shield the anemometer from the wind.
mm-hmm.
Affirmative.
Yeah, I would agree with. I would look. I think this is the point that John's trying to get at. Is I would look at least what your at any position that survival speed, what is your margin? If you have some margin, it's probably good. I know you've got a safety factor of 5, but you probably don't need safety factor of 5 if you assume that you're going to be at stow. But if you had a margin of 1.5 in any direction, that's probably sufficient for your survival spec, because you never know. You're going to depend on a human to go out there and put that stow pin in, and we're all human, and sometimes things don't happen that you thought happened. So
Well, and also you might lose power to your system, if you have an unexpected storm blow up, and you might not be able to get it to stow, and you don't want people going out on the roof in the storm. So there's a lot of things that could happen, and you don't want this 1,100-pound antenna being torn from its mount on the 6th floor or the 6th floor of the building.
Yeah.
Okay, understand.
All right, and so just a little bit more analysis on the counterweight arms, because they are rather large. Each counterweight arm supports 2 steel plates, so 4 total, each plate weighing 35.4 pounds. Analysis here was performed at the horizon position, just because that's going to create the largest moment about the axle. So again, A36 low carbon steel yield point of 250 megapascals. Under simulation here, we got a factor of safety of 5.33.
Sorry to interrupt, but when I went through the original slides, I didn't see any fastener margins. Did you look at the fasteners for mounting these plates?
So I used just SolidWorks bolt connectors, if that's what you mean.
Yeah, shear strength, bearing, bolt bending if you have that.
I don't have those currently on hand.
If you looked at it and you have, so let me cut to the chase. Are you material limited or fastener limited? When you define your margins, is it material yielding or is it fasteners shearing?
It was material.
Okay. That in general is a good place to be instead of being fastener limited. Okay.
Yeah.
Okay, so this is one of the first FEA analyses that we conducted on the mount. We wanted to see what the weight of the dish and gravity had on the mount before placing the forces of wind, and we got a minimum factor of safety of 9.42. Next slide. And this is a result for our operational wind speeds. The loads that we added on FEA was gravity, the weight of the dish, drag force, lift force, and the hinge moment. The deflection from the loads only result to an approximate 1.94 arc seconds of pointing error. These are our results for survival wind speed. Likewise, we added gravity, system weight, drag force, lift force, and hinge moment, and those are the values you see there. Our minimum factor of safety was 11.28. We conducted another test on the axle just to make sure that it wasn't shearing or failing, and these are our results.
Can I ask a question here? When you say hinge moment, well, first of all, is the large disc the brake or the gear?
Yes.
Mm-hmm.
Yes.
Is both the brake disc and the drive gear? Is that right?
Yeah. The brake disc is right there. We don't have the drive gear in on this little model. We were basically just trying to test what would fail first, the axle or the brakes.
Okay. And the hinge moment then is about, I guess, Rx. Is that rotation about X?
Yeah, rotation about the axle.
Okay. Thank you. Very good.
Okay, and these are our calculations for the brakes. This is the equation we used. Inertia torque only applies to dynamic braking. Frictional torque was assumed 0 for a conservative approximation. Our load torque was 419.12 Newton meters at survival wind speed. And for the braking force, we used this equation where Fn is the clamping force and mu is the coefficient of friction. For alt, our clamping force was 5,338 newtons at 250 psi. And so our braking torque was 747 newton meters. At AZ, the braking torque was 961 newton meters. And so our max load torque on the mount was 419.12 newton meters at alt, and with a margin of 328 newton meters.
So hate to interrupt, but this is a new slide, I believe, from what the slides that I saw before. Is this one of your newest?
Yeah, we've had all of these for a while. We weren't sure what we were supposed to be presenting the last time we talked to you guys, so we just put all of these in here from previous analyses.
All right, very good. Quick question: your mu you use for your coefficient of friction, that assumes dust, dirt, oils that might be on this disc after a few months of operation, or is the mu that you use an idealized mu out of a, well, what is the material and the mu that you assign? Maybe it's in here.
Elizabeth, I know you did that. You were the one who researched that.
Yeah, I think it was an idealized value. We didn't consider the oil.
Just to add for the friction, the top of the mount, if you remember the picture, it's open, but we have material.
Sheet metal covers.
Sorry, yeah, sheet metal that will completely enclose the top of that. So
we hope that minimize the dust and
it should be minimized, the dust and the water. It should completely enclose the brakes, the gears, etc.
Okay, I would flag this maybe as an area concern. I'll leave that to others, but you show a pretty low margin on your brake in your earlier slides. And you're going to be sensitive to that mu that you idealized for this calculation. So you might address that and look forward if it does fail, fully understand what the impact is if your brake fails. Do you fall to a hard limit? Do you back drive the system? I'm not sure. So just thinking safety, guys. Safety first.
I have a question about the values you've assumed here. Is the load at it says there, sorry, at survival wind speed. Okay.
Yeah, so when it's at this load, like the stow pin should be in it at this point, which kind of accounts for any, I think, extra margin. I mean, we have about a 50% margin. I wasn't sure where else you said it was different. If it is, it's just a typo.
Oh, we can go back to that later. I don't want to hold that presentation.
All right, so here's our system requirement verification. Everything is green is already passing. As you can see, that's a significant portion of that. The yellows are still to be determined. So first of all is our ingress protection. All of our subassemblies haven't been completely finalized yet, so we have no, we can't test the ingress protection quite yet. And lightning strike protection, we know that we need at least one lightning rod connected to the receiver once that eventually gets placed. None of us really know too much about lightning strikes, or like protection against that, so we are open to suggestions about that. But we do know we need at least one on the receiver because that's the most sensitive area.
Yeah, I have some comments in that regard. You should plan for it to be struck by lightning because it will be eventually. Mm-hmm. So you need to do things like use fiber optics on your Ethernet, things like that, where you won't conduct the electricity into the building. You got to put lightning arresters on all of the cables before they enter the control room and things like that.
Yeah, and if you can always get a lightning rod higher than your antenna, you're going to do better. So you may see if there's any lightning protection. I know they usually have ring around the parapet. Mm-hmm. I believe seeing lightning rods along the parapet of the building. But it's always good to have something higher than your antenna for the lightning to strike, if possible.
Okay, thank you. More system requirement verifications. A lot of these are electrical and already passing, have been discussed by Carrie and Chengri. The only one that's TBD still is our limit switch. Previously, when the telescope was in operation, it never was intended to go past zenith. So we just need to simply move the limit switch for elevation to account for us moving it past zenith into the stow position, which is a pretty easy mechanical fix.
I noticed that your servo motors each are rated for 800 watts. Are you planning to not run them both at once, full power? Is that how you can get away with 800 watts?
768 is the max combined of the two.
Well, if you look at the data sheet of the motor, it seems to be 800 watts apiece.
I don't think that's the case. 768 is the max combined of the two. Data sheets.
I'm going to go back a slide, Bridget.
I'm looking at the data sheet.
Or where's the motor thing? Was it on that slide? Oh, yeah.
4.5.3, right?
Oh, yeah, I see it. We can move on while you're looking at that.
Yeah.
Okay.
Next slide. And again, all of these are already more system requirement verifications, and these ones are already all passing due to analysis and inspection.
So this is the end of our presentation. So to summarize what we just talked about, so the radio telescope will be built with a new radio dish and truss structure and will be placed on top of a revitalized telescope mount. Computer and power supply sub-assemblies will operate the telescope as Chengri and Carrie have defined. Currently, right now, what we're waiting for is quotes from machine shops. We have gotten a couple so far, and once we get that, we'll be sending those quotes to Justin, and we'll be moving forward with that afterwards. And then we'll have the revitalized mounts and the software all completed by the end of semester or May 2021. And we expect this radio telescope to be safe to be operated by students, faculty, and the general public. And then we said we have questions. We have a couple questions. Shingri, do you have an answer to the power consumption question?
Yep. Let's see. One, the current. I believe we found it on the data sheet. 34H. No, not this one. Okay. 3, 4.
Do you guys have any other questions? Watching Greece still looking for that?
Yeah, I found it. I don't know how to share this information. Maybe I can share screen. I don't know.
Yeah, can we say it? Alright.
Yeah, so our motor is QCI34H3. The peak current is gonna be 315 each, and it's gonna draw in amps at most. So the two combined, that's within the capability of the 800 watt power supply.
Yeah, I was looking at the wrong column. Looking at the one next to it.
Do you have this information?
Yes.
Okay, cool. Yeah,
So-
our is a 34H-3.
Okay. So I had a couple of other questions on the drive system. Basically, the motors are way more powerful than the gearbox can stand. So you have to have a way to keep from breaking the gearboxes if you have a problem with your commanding, I guess you'd say. If somebody raises the acceleration rates above what the gearbox can stand, you'll need to beware that you could break your gearboxes.
So that would be changed in the code only. So it's not like only authorized people will be able to have access to the actual code.
The operator
So-
will not be able to change the acceleration and the velocity. That would be needs to be changed in the source code. And the other protection is the servo motor has a torque over torque protection. We can program it. If the torque is getting over, we can slow it down or shut it off.
Yeah, you definitely need to do that at the servo motor level, because you don't want your motors to be able to destroy your machine.
Yeah. Yes.
So I have a number of comments that I sent out to Victor and Carrie just before the meeting. I apologize. That's the only time I had to review your slides. And I want to thank you guys. That was a very good presentation. You covered a lot of ground. You did a lot of work. Some of these comments may have been handled by other people that have looked at this. And if so, that's fine. If you have an answer right now, you can provide it. If you want to research it later, that's fine. But I got a general comment, which is, are there any civil engineering requirements that flow down to what you're doing, what you're putting on top of Steward Observatory that will that need to be addressed? And what I mean by that, a 15-foot antenna, it's fairly massive on top of a roof, might have, well, a lot of sign-offs might be required, and I don't know what that sign-off train is. Someone else would be addressing that. But one of the detailed questions that comes from that general comment is, where did the 55-mile-an-hour requirement come from? Is that industry standard for radio antennas or that we use?
That was Mac's historical data in Tucson.
Okay.
Yeah.
And if you don't mind, I can go through this list, and Carrie, you can send this off to the design team.
I just got the questions from Carrie.
Yeah, I just forwarded it to Bridget.
Okay. So you're reusing existing equipment. Just want to make sure you've got some inspection criteria for that existing equipment that you're happy with, that the project is happy with, that you look at it as much as you need to call it good to put back into service. Okay. Just be aware of that. Their survival temp, you've got a max and a min that you derive a panel gap for, I believe. Okay.
The panel spacing was made so that the maximum possible thermal expansion of the panels, they're not going to crash into one another.
Okay. And that survival temp is what?
I think it was, I mean, I'd have to pull up my notes again, but it's I believe it was like a delta of 60 degrees Fahrenheit or something. It's like I think it was a 25 or 30 degrees Celsius actually. So kind of from 115 degrees in Tucson all the way down to 60 degrees at night or something.
Right. You assemble at room temperature and you looked at make sure they don't bang into each other. Very good.
Yes,
okay.
Exactly.
I didn't see in your analysis details what the forces and moments have to be reacted at the pad. So there you show there's an existing pad you want to interface to. What are the allowables that the pad can accept and have high margins? And that's something that your civil engineer or the building facility manager is probably going to want to make sure that you're good for. I didn't see those here, but you might end up having to provide those.
Justin, do you want to talk about that?
I do want to talk about that, and I'm hoping actually somebody, one of you can maybe help us out with some insight here. We have been talking with Mark Bugowitz, and he has raised this with FM and various other groups on campus. I haven't been able to find someone who can give me a drawing for that pad. I am still working. Brian Duffy is talking with the campus architect, and will hopefully be able to locate that drawing. I but we need to have, I've been able to find that the roof on building 65 is a concrete roof structure. But I need to know, how is that pad tied in to the concrete roof, and how thick is it, and how much rebar is in it, and all of that kind of thing. And we are going to have that reviewed by a structural engineer, the connection between the mount and the pad. But a structural engineer can't do anything until we provide her the what's in the pad, right? So if any of you have experience of finding as-built drawings for Steward, I would love to get some pointing or get some tips about where to go.
Hey, Justin, I saw that you had Dale Webb review this. Now, Dale Webb may have drawings because that was done for NRAO back, when they built the building, so.
Is that who the pad was made for?
Not the pad, but the actual addition was done for NRAO. And I know that Dale was very diligent in looking over the drawings as they built that specifically for NRAO. So you may ask Dale if he happens to have a set that the architect provided, or any information on that, because I know that he was looking at that religiously.
Thank you.
Now, as far as the U of A should have a set too, but you're probably in the right realm to be asking the U of A architect or PD&C on who has a set.
So I have a question about the power loss. I think John brought up a good point. What if the power to the telescope is cut off before we are able to stope the telescope? In that case, would you think adding a UPS to the telescope would be helpful? Because currently, all the gear train is kind of tied in, and we don't have extra room to put something that you can crank the telescope manually to the stope position. The only way to move it from, say, horizon to the stope position is by its own power.
If you can get an 800 watt UPS.
Yeah, those are pretty straightforward nowadays. That would be a good thing to do, because get a 1500 watt UPS and stick it in there. That's only a couple $100. That would be good insurance.
Yeah, if we tied a UPS into the telescope power, then in the worst case, the power is lost, then we still be able to stope the telescope. It won't be long, but only enough to stope the telescope. That's the goal, I guess.
Yeah. Do you have to stow it in azimuth as well, or is it just the altitude that's critical?
I believe the elevation is the only critical. Azimuth, we don't have any stow position for that.
You don't care if it.
Well,
There's a stow position because there's the bar in a certain location. There'll be 2 stow locations, 90-degree angles, but it has to get to one.
Okay.
In addition to Shangri's question, is there any other standard practices that we should take in the case of power loss before we get to the stow position?
No, if you don't have any way to move it once you're at stow, if you don't get to stow, then you just have to hope your brakes hold against the wind.
Okay.
So it would be great if we have an analysis of just for that situation. It's sort of like the worst scenario it can be.
Yeah, I agree with what Tom said. You want to have at least a factor of, or maybe Victor, that you want at least a factor of 1 point something safety in any position, just in case.
Yeah.
And I think I have another point here. The control room, the computer, that probably get another UPS system that will just ensure when the power is lost, we can always retreat the last known absolute position of the servo motor, so that when the power comes on, it makes the recovery a little bit easier, and just have a more insight of what's going on with the telescope.
Yeah, I had some questions about that. And again, I might be working with bad information because I haven't spent a whole lot of time digging into it. But the motors themselves seem to have a connection on them to be able to put in an auxiliary power, like a battery, to back up the position. I don't know if you've looked into that or not, because the servo itself, the electronics inside the motor itself has the ability, I think, to take in an extra voltage to hold its memory.
Yeah,
it might be worth doing.
I understand your point. That's actually a great thing because some modern servo motor, it has a battery on it, so it keeps tracks of it always know where it's at. But this servo motor, I believe it was from 2003. We looked through the data sheet. I don't think there's some sort of auxiliary power that can be hooked up to retain the absolute position. The only power to it is the main 48 volt. So that's why we want to have a UPS just for that.
Yeah. So along with that, if you say, for instance, you do, for whatever reason, somebody kicks the power cord out of the wall or something, and you plug it back in, and now the thing doesn't know where it is, what's the procedure for recalibrating the azimuth elevation so that you know where it's pointing?
Can you state the scenario again?
So for whatever reason, your power goes away when you're not stowed, or actually even if you are stowed. But if you're not stowed and the power goes away, when it comes back on, you don't know where the antenna is pointing. How do you recover from that?
So there's a couple of situations. So if the telescope is stowed, then that's great because in the software, we set the stow position as the home position. So all the motion will be relative to that. So if you want to stow the telescope, you just tell the servo to move to absolute 0. That's your stow position. But if you say the telescope is not stowed and you've got a power loss, even though the UPS fail, and that would be something interesting, then we will have to connect the power and then manually draw the telescope back to the stow position. It would be done manually using jogging. The software cannot take care of this.
Yeah, and just to add to Shane Gray's point, we currently have a program that saves the location of the telescope every 2 seconds, so we're able to recover the previous position within 2 seconds, and then by using the jogging feature, it should be somewhat painless to get it back to the previous location.
Okay, so that leads into the kind of the last question I had is about the accuracy requirements and how you're meeting them. Have you taken into account all the backlashes in the system? Do you have look like a chain drive going to a gearbox, which goes to another set of gears, and none of that's anti-backlash as far as I could tell. So it looks like you're going to have a lot of backlash in your system. Is that going to be okay for the task at hand?
So that goes back to the scopes, like what kind of object are we tracking? So we are planning tracking like sun and moon, so it won't move too fast, and I believe the motion will be always on one direction. So I hope is let's say the moon comes out of the horizon and it keeps going up, so that way as long as we are moving always in one direction, we can take care of the backlash. And the backlash on the elevation, we actually test using the servo motor to test that. I think it comes out pretty repeatable, say jogging one direction and jog it back. It comes pretty repeatable, but we're only using a construction level to do the testing. For more accurate testing, we may need something like a indicator or test indicator to see how accurate it is for a quantitative number. And the AZ, the azimuth one, that one got a huge backlash on the gear train, but as long as we are turning only on one direction, we can eliminate the backlash. And what we're thinking to do is measure the backlash, say how many turns of the servo is required to get rid of it, and then bake that into the program.
The problem with that is the wind might not cooperate with you.
Right, John.
Especially in azimuth. The wind
So
might
the-
push you.
Yeah.
Another thing that wasn't included in the slides is I'm planning to add an optical telescope, a small optical telescope with a camera to help with alignment as well, which will hopefully help us overcome some of those pointing issues.
Yeah,
If the backlash on the azimuth is really bad, you might want to consider fixing that, because that's really difficult to deal with. You could put an anti-backlash, just put a motor on there that drives in the other direction so that you're always pushing against another known force and not just kind of flopping.
we should also mention one other thing, that like when we originally set up this project with the system requirements, it was just to be able to, like, functional requirements, it was to be able to just drift scan it. So ideally, we just move ahead of the moon, put on the brakes, and the moon would pass through our field of view. So
Yeah,
it wouldn't be as big of a factor if it was going to be used for a simpler manner like that.
that's true. I saw that in the specs. It was for drift scans, and this is not a factor in that case.
Yeah, but if we want to do stronger tracking in the future, that's definitely a really great thing to be aware of.
So I've got one safety related question. You guys might have done this. If not, I suggest you do. And that is worst case inertia loads on your structure. And that could come from an operator max jogging at whatever max jog speed you allow them to operate that during integration and test. Possibly this is where you're going to find a lot of issues come up. Let's say someone's troubleshooting max jogging the system and they have to hit the e-stop. So at the max speed that this system is allowed to drive, and you hit the e-stop, what is that inertial load through your structure and into the pad?
Okay, so I think you're saying if the dish is moving at its max speed and all of a sudden somebody hit the e-stop and then the dish will stop, then what is the inertia of that and what effect it's going to have on the structure?
Correct.
Okay, let's...
Yeah, we haven't done any sort of dynamic loading scenarios like that, just because as Mason, we're drift scanning, so it's a lot of time in operation. It's going to be stationary, but yeah, that'll be a good thing to look at.
I understand, yeah. But I tell you what, you're going to really challenge the system when you bring it up and do your integration and test. And that's where you'll have people around and maybe overlook, well, just understand yourselves what you're doing to the structure for the worst thing your people could do to it.
Yeah.
Okay.
I have a couple of questions. You mentioned earlier the bolt analysis on the counterweights. Did you also do a bolt analysis, say, on the mount where it bolts into the pad?
I think that would be Lisbeth for the pad analysis.
Yeah, we simulated it on SolidWorks and it was passing.
Okay, and then the support structure is all the 836 steel. What treatments are you doing to that, I guess, to protect it from rusting and whatnot?
We haven't quite discussed it, but I mean, I believe the kind of typical thing is to paint it and paint it white for both, heat mitigation and for rain protection.
And 80% or say 90% of the existing hardware, it already has a coat of white paint on it. We might have to fix some spot where they miss it to make it like look good and seal good, I guess.
Mm-hmm.
Oh yeah, another question adding to the bolting thing. Elizabeth, do you know what grade of the bow you're using, say grade 8 bow or better? It would be great if you have that information and makes this more convincing.
Yeah, we need to double check that again because we just been using bolted contacts in SolidWorks.
Yeah.
Yeah. I think the default for SolidWorks, the yield strength of the bolt is somewhere at 700 or 800 megapascals, if that helps. That's the default I would imagine we were using.
Sounds good, thank you.
And yeah, in terms of electrical, I have another question. Let me bring up the schematic. screen share. So currently we have, so this diagram is what we plan to do, but as of now, annotate all this switch, there would be after the clamp module. I don't know if that's a good idea, because if you stop this motor, it's going to generate back EMF, but with the switch in the way, there's no way for the motor to dissipate those energy.
Yeah, I think you're right. I don't know that module, but what you say is correct. You need to have the switch on the input side of it.
Yeah, I think the diagram I have here, it would be ideal, but currently these two would be after the module, and I don't think, well, it's probably not the best practice. They had this setup from before. I think they worked for them, and they did not tear the motor apart, but probably for best practice, we're gonna move those switch before the clamp module.
Yeah, I think that's a good idea. I don't think it wouldn't over torque the motor or anything. It just wouldn't, the braking wouldn't get any dynamic braking, and you get a lot of excess voltage in the motor.
Yeah, it's probably not good. They mention it on the user manual, and they can fry the electronics.
Right.
And I guess the other question is, I don't know, I just used KiCad to come up with this diagram. You can see this is supposed to be a USB connection, but I just boiled it down to one wire. I don't know, do you have any suggestion on what kind of software we could use to make like what they would use in the industry? I guess that's how I asked.
Well, there's a lot of different things in use at Steward. We use OrCAD, and we use Altium.
Altium.
Yeah, and a lot of people at LPL actually use KiCad, which is a free system.
Yeah, I believe this is what I'm using, KiCad here.
Yeah.
Okay, good. Thank you.
Are there any other questions from the panel?
I have one, if everybody else is done. Since I'm part of the safety committee, I actually had submitted you guys some questions earlier, and I had brought up the idea of a modal analysis. Did you guys ever do one?
What analysis?
The modal analysis.
Vibration.
Oh, vibration.
So I think the feedback for that was that there, since it was only supported along the arms, there was no support in the other directions. It was subject to frequency. Is that what you meant by the modal analysis? Why we needed to do that?
Well, that's part of it. So when I was going through your initial slides, I noticed that the way the arms were supported didn't look awfully robust in an orthogonal direction to their arm geometry.
Yeah.
That leads me to believe that there's likely some kind of shake going to happen at the counterweights. But the same can be said for pretty much all of the extended structure. So a general modal analysis of the entire dish support would give you an idea of what your ringing frequencies will be and whether that will have an effect on your optical resolution. So I'm not an optical engineer, but I have some optical experience, and I know you have a full width half max requirement for resolution, which is actually fairly large at 6 degrees. But you guys could end up with a case where your modal response of the system is something in the 1 or 2 hertz range, which could really greatly affect that angular resolution. Especially when you consider, like in your control system, if you're at full velocity slewing to an object and you stop to do a drift scan, what's your settling time at that stop location? You know, when you issue the stop command, the gear stops moving, but there will be some vibrating resonance that happens as a method of that stopping occurring. And that will lead you to some sort of settling time to get to a point where you're actually having some sort of less degraded frequency input to the dish. Again, I'm not an optical person, and I don't know how that affects radio per se. I work mostly in visual telescope design, but it's something to consider.
Yeah, 21 centimeters with this small of a dish, it's not a big deal. Like you said, they got 6 degree full width half max beam.
But even
Yeah.
beyond, oh, sorry, I was going to say, but beyond just the incoming beam characteristics and what that could do, vibration over time or vibration during motion could have adverse effects on the way your servo system works too.
Okay. Yeah, I think we read your comment. We're definitely trying to figure out how to go about doing that right now. I think Jared or Justin or someone gave us some ideas of how to go about doing that. With just Jared, unless you have questions, I guess for the modal analysis, the vibration you're concerned about, is that, you said it's just vibration due to motor rotation and stuff, or is it vibrations of other potential that could cause issues?
Well, I think you can split the vibration characteristics up into their independent cause and effect solutions, right? So you'll have some cause, like running your servo system will set up some ringing frequency in the structure that will likely be completely independent of the wind effect setting up some ringing frequency in the structure and could be in a completely different direction. But in some cases, you may find that there are instances where you're running at a particular velocity or tracking at a particular velocity, and then the wind picks up at that same ringing frequency. Now you've amplified your vibration characteristics. You actually will see more motion in the structure. I know that that's a vibration analysis and modal analysis of the system tends to be a pretty advanced, I don't want to say advanced, it's a necessary analysis to perform to understand the characteristics of the system, but it can start to run away from you in terms of understanding your boundary conditions and your loading inputs to the system. I mean, you do have to understand your motor frequency operation, your servo system frequency, make a guess at some wind loading characteristics, and you end up with lots and lots of use cases and loading cases that ultimately contribute to the overall performance, expected performance and behavior of the system. It's a lot to do, and it would be interesting to see if you guys could head down a path where at least, you do maybe a couple of those base use cases where you're looking at either just a wind component or just the servo component or something, just to understand what the effect on the system is.
Okay. Thank you.
Good point, Carrie. Does anyone have some target values for their minimal fundamentals that they should shoot for or be aware of? So you've got the tuning fork from the counterweights. Is that one of the things you were addressing, Carrie?
That was the first thing I addressed, yeah. Just because it looked to me, the visual inspection of the drawing just made that look like it was a tuning fork.
I agree.
One other thing I can speak to for that, it wasn't present in any of the pictures that we showed, but they're actually cables. So if you have the counterweight itself, there's cables running somewhat at an angle to the counterweights. So it's not just supported on the arms, there's also support coming in from the other directions due to cables. I don't know if that'll get rid of all of it, but.
Yeah, so.
Well, it will help, yeah.
To Carrie's point, yeah, the narrow cross-sectional diameter of your truss work, yeah, that's probably where you're going to see or maybe it's bending. I'm not sure by looking at it. But yeah, finding what the first non-rigid body mode is of your structure would probably be helpful to know. But that's only as good as if you know what you need it to be. Otherwise, if you don't have a target goal, then and you don't want to fall into the rabbit hole that Carrie was getting into, that you can just suffer paralysis by analysis, not knowing what your goal is, doing modal or dynamic analysis. Plan on some time during your integration and test when you do your build to actually run through and fully understand it. Make sure you're not sensitive to it.
Yeah, that was one thing I wanted to kind of make clear is the issue with our team is that we're, graduating in a month. We're not going to be involved in the integration and build with this at all.
Now that's going to fall to John.
So we're trying to do everything we possibly can to make sure this thing's safe, structurally secured before it's built. And I think that performance, and Justin, you can correct us on this, is a secondary goal kind of to safety.
Absolutely.
Um,
Yeah, if we lose a week of observing on this, it's no problem.
yeah, because I mean, Justin, correct me if I'm wrong, but you guys can make improvements to this in the future. If you find in the future that the vibration affects pointing accuracy or something, it can be modified.
Okay, I think I have another question. That's for the stop procedure. So for now, if the software e-stop is pressed, then the motor is gonna stop at the deceleration where it accelerated. It's not gonna come to a full stop instantaneously. It's gonna have a pretty gentle deceleration. Would you all suggest it should come to a full stop instantaneously, or it should be decelerated slowly, or for a given deceleration?
If somebody hits an e-stop, you want it to stop now.
But at the same time,
I was saying the
a button on the
software e-stop.
Yeah, you should probably not call a software button on a GUI an e-stop. It's a telescope stop button, but you can't really call it an e-stop because it doesn't actually connect to anything hard like a hard e-stop would. Okay. So the stop on the screen should not be considered an e-stop because who knows, somebody might have cut the Ethernet cable.
Okay.
But it's considered a stop button, and you're correct that it should be a nice controlled stop.
Okay.
Versus an e-stop, which is generally pretty violent if your telescope is moving at any speed.
Yeah.
Yeah, I think of the e-stop, maybe it's a safety thing. So somebody's hand is in the way or whatever. You want it to stop right away.
Yeah. And an e-stop, you can't say an e-stop is a thing on a computer screen. So you don't want to even get in the habit of saying we have an e-stop on the screen. You have to have a hard button, and that's your e-stop. Which you've got two of them, so you're good.
So if I understand what you said, you wouldn't consider the telescope stop on the GUI a safety feature.
That's right.
Okay.
It's an operational feature.
Okay.
And your hard buttons on your control cabinets are your e-stops.
Okay. Yeah, that will raise some interesting question because I think there should be a way to know if the e-stop is pressed, because if the power to the servo motor is loose, then the shaft can just rotate wherever they want. So we also want to activate the brick as soon as the e-stop is pressed.
You can generally you can get an e-stop with more than one set of contacts on it, and one set of contacts can feed back into your computer.
Okay.
And that's what we usually do for real.
Okay, that's a good point. E-stop feedback.
Same thing with your limit switches. You can get limit switches with multiple contacts that you can feed into the controller, and that way the computer knows that it hit a limit. Even if it doesn't think, if somehow the angle's off on your encoder and you drive it into a limit, it'll just stop and nobody will know why unless you have a feedback from one of those limit switches.
Okay, yeah. In terms of the limit switch, that's good point. Because at the beginning, I thought because currently the elevation limit switch, they are wiring directly to the power of the servo. Earlier, I was thinking change those, and then when they trip the limit switch, they send out a signal to the computer, and the computer stops the motor instead of a hard stop. But if I understand what you say, I think hard stop is preferred in this case. Yes,
it is, because your computer might not listen to the switch and your thing will continue to drive past the limit.
Okay.
Also, do you have hard limits on your machine where if for some reason everything fails and you try to drive it past the stow position and just circles around? Is there something hard that'll stop it? If not, I think you should consider that, because
it's more like mechanical features.
Yeah, mechanical stop, a hard stop.
In one direction at horizon, the receiver is inches from the ground, so they would just kind of hit the ground there. In terms
Yeah,
of
but
kind of going
that's
past zenith, I'm not sure how we can do that.
letting your receiver hit the ground is a bad thing.
Well, receiver arm, the receiver itself.
Yeah. Well, I mean, the arm, you could probably bend it since it's so far away from the dish. You might bend that whole structure.
I don't think we have any hard stops, but
yeah.
Yeah.
And the reason I'm bringing these up is because you said you wanted this to be safe for astronomers and the general public to use. And until you can have all of these sort of belt and suspenders things, it's not safe for the general public or people who didn't actually build the telescope to use. You have to have it where it's, you know, foolproof. And fools get more ingenious all the time.
Everybody, they'll find ways.
Yeah.
To system that you didn't think of.
Yeah. We come up with a lot of situations that we never thought of.
Yeah.
So that, I think that's a good point.
So I worked,
you know,
before I
Go ahead,
came to the University of Arizona, I worked for the National Radio Astronomy Observatory for more than 20 years. And
Wow.
I've seen it and seen a lot of bad things and seen a lot of good things happen. And that's why I'm giving you some of these questions.
Yeah, and so, you know, the azimuth limit switches, John is right, because, you know, the last thing you want to do is rip out all your cables. And I don't know what your limits are. How far can you go before you start ripping cables in the azimuth? That's something that you really want to know. And then you want to put your limits well before you start doing that, because, you know, it's probably not weeks of downtime.
Right.
Yeah, that would be a great question, actually. So how do you detect? We know from the motor, we know how many turns it has turned around, but how do you integrate a limit switch that can do that? Like trip the circuit after it has been turned so many times.
That's an interesting question. Yeah.
You put in a topple block and a turn indicator. So as you go past a full 360, you have a cam that slides over to change the switch to a different switch activator.
Okay. I see.
And then for a physical hard stop, you can put in a topple block where you essentially have a block set up, and as you pass 360, it turns the block over sideways so that on your next pass, it will actually physically stop. And then in the reverse, it does the same thing. Usually call them a topple block.
Okay, so it would be some sort of cam
yeah, and
device.
Shigri, there's a couple small holes around the rotation axis that I think we'd be able to screw or at least epoxy things like that onto.
Well, you want to make sure your hard limits, I think that's what John's getting at, and Carrie, if I understand that, the hard limit that you want to put in to prevent over rotation has to be able to tolerate your full stall torque of the motor.
Oh, I thought she was talking about electrical, sorry.
She's talking about both.
Both,
Oh.
yeah.
Right, right. But a hard limit is, I think, as John was saying, very, very important to have to protect your instrument.
Okay.
And size your components for the absolute max drivetrain torque that piece is going to see. And hopefully your drivetrain should be designed to accommodate, to stall your motor. Last thing you want to do is drive to a hard limit and not be able to drive off of it because you broke your drivetrain.
So how do you recover from it if you trip the limit switch?
Yeah,
You manually drive it out. You override. Somebody has to go up there and push a button to override the limit switch to drive it back out the one way. You can also get clever to say that the motor can only drive one way once it's hit that limit switch, and that's back out. But if you don't want to get too fancy about it, you can just manually drive it back out of the limit.
One thing to remember is you have to be able to disengage the brakes if you're going to do it manually. So if you kill all the power and the brakes are set, now you've got trouble.
Okay. So
there's a lot of details that go into these things.
Yeah, John, your comment about you've seen it before. I think both Victor, yourself, me, Carrie, this comes from many, many aggravating late nights troubleshooting systems trying to just drive off a limit.
Yes. Driving out of limits is a nightmare.
But the last thing you want to do is drive off a limit or push it off a limit because your drivetrain's broken and now your system's down. Now you can't drive it. So
And what Tom said right there in terms of driving out of limits, this is also, when I submitted my questions to you guys before, this is also why I brought up the idea of being able to manually deactivate the brakes without power and to manually crank the telescope, because in some cases that is your solution for driving out of a limit, is to be able to physically disengage the brake without having to power, because energizing the system tends to become a safety hazard. If you can do that without energizing, that becomes something that's simpler, but it is more complicated.
Oh yeah, I think that's a good point. If you're able to override the brake manually, then you're probably doing something like cranking the telescope by your hand. That's the thing I brought up before, because for now, it's very difficult to say get in there with a wrench and turn the telescope, because the gear train is stops you from doing that. If you want to be able to turn the thing manually, then you have to physically disconnect either the gearbox or the servo motor out of the way. That way you'll be able to turn it. Even that, it'll be very difficult because the LZ, it has a lot of weight on it. Turning that manually is probably not a good idea. I don't know.
And it actually, this discussion brings up something I made a note of while I was listening to your presentation. I want to reemphasize the point that Tom had originally made about oversizing your braking system, because I think that if you don't have enough margin on your brake capacity to hold the telescope in your, say, your worst case storm condition, and you have it stowed, so you have your stow bar in, you have your stow pins in, and if your braking system isn't holding the telescope well enough, it's possible to jam the stow bar, right? If it starts to slip on the brake and you jam the stow bar, and if you can't unbrake and you can't manually drive the telescope, you may not be able to get that stow bar out. I've seen, it's rare, but I've seen a couple of instances where we parked a telescope in altitude and put the stow pin in, and for some reason something slipped and now the stow pin's jammed, and you have to be able to back out that particular axis so that you can get that stow pin back out of it.
Is it like back out manually by hand?
Well, in the cases that I've dealt with, yes, the telescopes have always had a manual crank on them in both axes in some way so that they could be manually moved. It's not a simple thing. Like I said, it was always an added gear, like a hand crank gear set on, say, the altitude axis, that you could disengage the brake and then manually crank the telescope a small amount. You know, the telescopes are balanced. I'm assuming you guys have yours balanced. You should be able to push it around by hand very easily.
Yeah.
If you don't have your motor limiting your ability to do that. So
Yeah.
if you have a way to disengage and manually crank, then that can help.
Can you manually backdrive the assembled system, backdrive the gear train?
I don't think so. You can probably do it with the altitude, but you're risking turning the servo motor in a very high speed due to the gear train, and because the clamp module is before the switch, then it can damage it. But we can sort that out later. But the risk is it can turn the servo motor at a very high speed, and it probably takes a lot of effort. That's for elevation, but azimuth, that's probably impossible because we have a massive gear reduction there.
We'll have to do some careful thinking about which of these failure modes are safety issues and which are just operational issues. Because if we have to, miss a month of public lecture series, that's not the end of the world. And it may not be worth spending, a few $1,000s of adding extra features, you know what I mean?
Yeah.
But if it is a true safety issue, then you certainly need to take that into account.
I think the only thing that is really safety related is whether or not the structure would fail if it was stowed out of position, if it was just lost. If position was lost and you couldn't stow it and you had this 55-mile-per-hour wind, would it fail?
Yeah.
And I think the rest of it is all operational.
A 1.5 factor safety in that scenario is kind of a good metric?
No.
One something. You got to have at least.
Yeah, greater than one.
Gotcha.
Yeah, I'm just curious. Is the first time your telescope will be fully assembled, will that occur on top of the Steward Observatory building? Or will you, okay. I see Mason nodding his head. All right.
Yeah, the
Justin, you
mount
can-
is already in N601 and it's quite heavy. So
Yeah.
it would be a lot of work to haul it down the stairs just to bring it right back up.
Yeah, I'm pretty sure when the telescope is assembled, we will not be here. Maybe at least for me. Yeah, I think that's all the question I have. So let me think of any.
So we're down to about the last 15 minutes of our 2-hour allocation here. Any other questions popping up from panel members that we haven't addressed yet?
I just have a comment that Justin should make sure he gets all the models that these guys have produced
For sure.
so that he can play with them later.
Yes, please. We don't want to hunt you down at your new job.
Don't you worry. We have all the CAD models pretty well organized in our Google Doc, so we'll or Google Drive, so we'll get the most updated version to Justin when we graduate.
Yeah.
The FEA models too.
Mm-hmm.
Yeah.
Okay.
Okay. Well, I think I want to say congratulations to you guys on both your graduation and this senior project. I'm absolutely amazed. This is wonderful. It blows my senior project out of the water. Wish I had done this one.
It's been a challenge.
Yeah.
Yeah, I think it looks really good.
Yeah.
Do you plan on observing with it?
I hope so.
Yeah, hopefully.
Yeah.
Good.
Hopefully Justin can set up some sort of website that allows you guys to look in on it from time to time and say, hey, I did that.
A blog post, maybe.
Little GoPro, look at the telescope.
Yeah, and actually that's what I have on the Bio2 telescope. They have a little webcam pointing at the telescope so they can know if anybody go in and if anything breaks down. You have a visual feedback.
Yeah, that's a very nice thing to have, but I think that's probably something left to Justin in his implementation on the next team, I would assume.
Okay.
So in addition to congrats to you students, thanks to the panel members. I really appreciate you guys lending your vast years of knowledge and assistance to the young students and engineers to be. I think we've done a really good job of passing on some knowledge here that should take them into their future.
Glad to help out.
Yep.
Thank you
Good
very
job,
much.
guys.
Thanks
Thank
for
you.
you guys.
Thank you very much.
So as
Bye.
as a closing sign here, then Bridget, since you're the team lead, I sent over Tom's questions. If you guys wouldn't mind preparing just a short answer sheet on those, similar to what you did for the safety ones, I think that would be good. And I can compile all those together with the notes that I took on the questions that popped up live here and submit them to both panel members and the student team so that you guys have an understanding of what we talked about and what you're looking at moving forward.
Sounds perfect. I got them, so we'll start working on that as soon as possible.
Excellent.
Cool.
Okay, well, thanks everybody. Appreciate it. Have a great rest of your Thursday, April Fool's Day.
Bye.
Thank you.
Thank you.
Thank you all.
Team, if you want to get into my Zoom room.
Yeah, let's hop in yours for a sec.
Bye.
Bye, everybody.
Bye.